something that we did last year that was related to Ken's presentation, because I think that's a wonderful segue, and I wanted to actually present on that topic today, but you know how life gets in the way to do them together, and I thought perhaps gears and transmissions are always a useful thing, and hopefully you'll get a lot out of that. But before we dive into that, so first of all, how many of you were here for the previous presentation on pneumatics? Okay, so we got a good crowd, but we have a lot more. So I'll just review and say that Ken talked about the climber that they built last year, which was you came up to a platform, and then to get up to level 3, it's the high lift, and I don't remember, 19 inches? Okay, and it was a beautiful system because they had 2 pneumatic cylinders in the back, which provided the lift, and at the same time it was pulling on a brake cable, which was pulling an arm in a coordinated way that lifted the front up. It was a really nice and elegant use of pneumatics. And Ken rightly noted that you wouldn't want to just put 4 independent cylinders because you have instability of chaos. In fact, we saw several people with 2 independent cylinders just in the rear, or maybe some people did it. Maybe they did front and rear, but they were tied side to side. But even 2 with that number of degrees of freedom, it still didn't look workable, at least without alternative measures. That said, we actually did 4 independent cylinders at each wheel, and we made it work successfully. So how the heck did we do that? So what we did, and the reason we did it, is because we were very constrained with our design in space. And at the end of the day, for the lifting mechanism, we were given just a few inches of space around the corners of the robot to build something. We're like, well, what can we do with this? We weren't allowed to tie the legs together or anything like that. There just really wasn't the physical space for it. So what we did is we put a mechanical control system, if you like, onto this pneumatic system, because by itself, without anything else, as Ken says, no matter how much you try to tune that out, in software and dial in resistances and things like that, you got an unstable system. The robot, would tend to fall in one direction, right? And it's a reinforcement loop in the wrong direction. So once you start tipping, you're in trouble. So what we did was we tied strings, like heavy, small diameter but high strength cord on the bottom of each cylinder. So as it was pushing out on the leg, it would be pulling essentially 4 strings, so 1 for each leg. And we grouped all of those strings together, and we basically held them back so that if any one leg got ahead of the other, there would be enough force in the system for the others to wait to have to catch up. So and the damping system that we used for that was just another cylinder. We took just a cylinder that was dead, so unpowered, with a restrictor valve, and it was started in the compressed position. And at the end of the game, when we fired the lifting cylinders, all the four legs would come down, pull on the strings, and they were all connected to that one cylinder, which had to come out at a metered rate. So no leg could get ahead of the other. And we were a little bit late in getting it together, and where we struggled was, having the pull, getting pulled effectively on, because we had the lifting system, but then you had to actually pull yourself on. And we eventually got there, but it was a little late in the season. We had an arm ultimately that came down and latched and had a roller, and that doubled as our ball intake. So anyway, so just wanted to mention, you can do crazy things, right? This is one of those tricks that you mentioned, like there's a bunch of tricks and things that you could do with pneumatics, and I would definitely categorize this under the trick category. And as I said last year, I never want to work with strings again. So it worked, it can work. Do you want to have strings running all over your robot? I don't know, maybe not. If you have other options like Ken's, it's probably a better idea to do that. Okay, so thanks for indulging me for 5 minutes here to talk about that. And maybe we'll write that up and present that at some point. But we're going to dive into the topic at hand, which is motors and transmissions. So we'll start with discussion about electric motors. no details about how the actual motors works, you know, not the electrical physics, but from a mechanical characterization standpoint. And then we'll talk about simple gear systems, transmissions, things like that. William, would you please advance? So let's just explain the concept of torque, because we're going to be talking about that. You know, motors are rated in terms of torque, right? So torque intuitively is some kind of a twisting force. It's a force, you know, acting at some kind of a distance. So if you've got a wrench and you're putting all of your body weight on it, like 170 pounds or something, and it's at a one foot distance from the bolt that you're trying to turn, that's 170 foot-pounds, something like that. William, can you go to the next one? So, and we're going to talk about power as well. So it's important to understand the difference between torque and power. So torque is the twisting force. It's a force. So it's something that's you know, independent of the rotational speed. It's the maximum twisting force that can be developed at that operating point. Power actually depends on speed, because if you can generate a little bit of twisting force, but you can do it a lot more often, then you can get a lot more power. So power is directly proportional to the torque. So if you increase the torque, you're increasing the power. And you'll see these kind of curves for like gasoline engines, right? If you're a car person, you'll see torque curves and horsepower curves. And I really don't like axes like this, but you have to interpret the power as, you know, this is in horsepower numbers, and this is torque, you know, as in pound-feet numbers. So it's kind of like combining two plots into one. And you could, for example, get the same power out of a very small, say, gasoline engine that you could out of a really large diesel. Like I have a tractor that's, you know, a very large tractor, and it's only 23 horsepower, but it's, you know, it's a diesel tractor, and it makes 23 horsepower at like, I don't know, 1,000 RPM or something. It's just very strong and runs very low speed. You could get 23 horsepower out of a very small gasoline engine, but the thing would have to run, you know, really, really quickly to do it. So that's kind of an intuitive difference between torque and power. William, would you? So now, getting back to, you know, electric motors like we would use in robotics, we can think of the motor operating along a curve like this, starting with the motor torque. Although I'm showing it's another one of those combined plots, torque and current. So think for this torque for this one and current for this one. The way the motor works is it's very simple. It makes maximum power at zero speed. This is the angular speed. So we'll think of it as, I should stop touching the screen perhaps. Is that me? No. Maybe it is. I'll step away. So it makes maximum power, you know, at 0 RPM. And then at some point, it's just spinning free. It has no load. It's spinning over here, right? It's not making any additional torque, but it's spinning away at a maximum RPM. So it's pretty much a linear relationship like this. So it's, in theory, pretty easy to analyze. So, and this line is the current draw, and you know it doesn't go to zero here because it costs you some current just to spin in free space, but otherwise it's totally analogous to the torque curve.
Just to clarify though, it's really not generating any power at free current, free speed, and free current.
No useful power.
Right?
Yeah.
Yes, it's consuming power.
It's consuming power.
It's overcoming its own, you know, friction.
But you said maximum power, but you said maximum power at
Say
free
that.
speed. I don't think so.
It's maximum speed at zero load.
Right. Just to clarify.
If you just
said
connect,
speed, or you just said power.
What you meant to say is that when you're going at maximum speed, there is zero mechanical power
right.
being available to you.
Yeah, you get maximum power when you've driven the motor all the way down to its stall state, which you don't really want to do.
Maximum
electrical power.
Torque, sorry. Yeah, I think I probably said this last year too. Like, I am the guy, I do this all the time. You know, I say precisely the wrong word at the wrong time, just to keep everybody on their toes. So Thank you for keeping me honest. So William, did we lose? I broke it? You want to fire it up again?
And Jim, I think what you're saying here is that rookies should know that if you have a 10,000 RPM motor, which is maximum speed 10,000 RPM, it will never do any useful work at that RPM.
Yeah.
Because it has zero mechanical power available.
Yeah, any load that you put on it all will drive that RPM
Yep.
down,
Yep.
right? And that will continue. The more you load it up, it will go down to 0 RPM, and ultimately it'll stall, and then what will happen? The magic smoke will come out.
Yeah, exactly.
All right, so, actually, wait, can you back up to the previous slide? So I did want to just show the equation, because this kind of pops up again, and we're not going to get bogged down in the details, but this is a pretty simple way to write the torque as a function of RPM, because this could be RPM as well as, I wrote it as omega, which is rotational speed. Typically think of it as dimensionless. Dimensionless radians, or radians per second. Seconds is not dimensionless, but the radians is. So, and you could write the current in a similar fashion, but of course we have a non-zero x-intercept there. Okay, can you flip? So, if we look at the current, we also have to contend with the fact that we may have this curve, but we do have breakers in the system, right? And we're going to do a little example here in a few minutes, not right now, but we typically have a breaker to work with, and this is probably a 40 amp breaker right here. This is a 40 amp breaker, and so while the motor may be capable of much more than 40 amps, we can't do more than 40 amps continuously. And we can do it for a while, and I don't know what a while is, because I haven't experimented with this, and I'm sure Ken probably has, and others may know.
On the quick resets, I think it's a matter of seconds.
Yeah, if you look at the
seconds.
If you look at the data sheet, it's
Yeah.
like almost a minute if it's over 50% over or something like that. So it's actually pretty substantial.
Well, sure, it depends too on the current draw, right? I mean, it must depend on the level that you're at, because if you
Yeah, it
start
depends on
drawing 200
the
amps,
temperature. So if it's like
it's
if
going to
you're
be
like
much
50%,
faster.
If you're like 50% over, it shoots faster.
Yeah. Anyway, so there is some ability to pull more than 40 amp continuous, but the point is you shouldn't design for that, right? And I'll talk more about that later. We've actually been been burned by pulling too much current. So go ahead, William. Next slide, please. So we talked about the relationship between power and torque, and at least if you use nice SI units as God intended, right? not these terrible US units that we also use, then power is simply torque times angular speed, right? So all we have to do is take that expression that we had for torque, multiply it by the angular speed, and we get power. And so we had this really nice line, and we multiply it by, which is our torque. I'm trying really hard not to touch this. And you multiply it by the angular speed, you get this nice curve here with a clear maximum, at the top, right? So, and then it's interesting to ask, well, where does that maximum occur, right? That's the maximum power that you can get. There are probably several ways to solve this, but the easiest is if you've taken calculus, right? You take the derivative of power with respect to angular speed, set that equal to 0. Where's the slope 0, right? And you find out it's at the halfway point. So you're half of the speed range of the motor. So that's pretty easy. It's like Ken being intuitive about what was that magic spot to set your starting point, right, for the pneumatic cylinder. I would have guessed a half, right? I mean, it seems like a really good guess. Same way exactly here. So then of course you can calculate what the power is, at that point. And again, we have to be respectful of the fact that that may not agree with our 40 amp breaker, right? You may be limited by that you may be drawing a much more than 40 amps at that maximum power point, and that's not going to work for the long haul. So next slide, please. Okay, so again, thinking about respecting the 40 amp situation, if you want to know, what those limits are, so what is your torque, what is your power and rotational speed at 40 amps, you can just use the expressions that we had on the previous slide. Just plug in, 40 amps, and you get your values. William? Thank you. So let's just do a quick example here, a numerical example. Can you move the mouse a little? Thanks. So these are numbers that are, you know, in the ballpark for kind of motors that we have first, RC here. So about 2 Newton meter motor, you know, 5,300 RPM, 3-speed. So this is a slow motor, right? Some of them, like the 775 we have around somewhere that we're going to show is, I don't know, north of 20,000 or something like that. And then this is the free current here start at the bottom, which is operating in open space, right, with no load. And this is let's see, intercept, it's maximum draw. So if you wanted to calculate, you know, the speed at 40 amps, the power at 40 amps, and the torque at 40 amps, just follow the expressions. We won't go through the math, but you know, everything you had on the previous slide, you plug in the values, and there it is. And if anybody gets, I was detailed here because if we share these slides with people, I want people to be able to work an example. It's less fun to go through that in person. So we go ahead. So we talked about motors, and just, you know, in summary, the important thing is you're thinking about torque with an electric motor, right? That's kind of what's guiding everything, and you've got this nice linear approximation of that performance. And typically, the manufacturer's data will give you the maximum torque, which occurs at 0 RPM, and the maximum RPM, which occurs at 0 torque. That establishes your line, and from that, you can build everything else upon it if you just use this math, where you can figure out the power at any RPM. And I'm going to show you an example later of a spreadsheet to do these kind of calculations. But it's also fun to consider not just running the motor by itself, but running the motor through a transmission or some kind of gearing reduction or something like that. So, so that's the segue into gears. So now we'll go back and start simple, you know, on the gearing. And we'll talk about simple gears, or actually they're called spur gears, when they're just, you know, kind of the regular gears that you're used to thinking about, as opposed to bevel gears and worm gears, things like that. And I'll give you some examples of those. But if you just have gears, and we're gonna forget about the teeth for now. We're just gonna have 2 cylinders, you know, rotating next to each other of different diameters. One thing that we can say for sure is at that point of contact where they're rotating, that velocity, the tangential velocity, is equal, right? And that's the key to figuring out gear ratios, because that tangential velocity can be expressed as the radius times the angular speed. So for the cylinder 1 and cylinder 2, we have that tangential velocity is R1 omega 1 and R2 omega 2 respectively. So you can form the ratio like that. So the speed increase or reduction that you get, you know, when transferring power to, you know, a secondary, in this case, a cylinder, a wheel. And that depends on the ratio, only the ratio of, in addition to your own speed, the ratio of the diameters, right? It could be diameters, it could be radii, it doesn't matter, right? It's just a factor of 2, and that cancels out. So in this case, as a hard example, if cylinder number 1, this guy, is moving at 100 RPM, as shown here, then cylinder number 2 is rotating at 200 RPM, right? Because we have a 2-to-1 size difference, right? And this is smaller, it's going to rotate faster. Okay, so another truism, in addition to that point of contact, you know, where the velocity, tangential velocity is constant, is the fact that you've got the same force at that point of contact, right? There's equal and opposite forces, and this is true in, you know, most cases. If there's some crazy acceleration or something going on, that's not true, right? Because Newton's law is F equals ma. So if there's no acceleration, this is largely true. And we know, as we said on the very first slide, torque is a force acting at some kind of distance. So it's force times the radius out to that point of contact. So that's true for this cylinder and also this cylinder. And we get the same type of ratio as we did before. So relating torque is just like relating speed, except they work in an inverse way, right? So in this case, let's say we had 20 inch-pounds on that large cylinder. We're only going to get 10 inch-pounds out of that smaller cylinder, which is only half the size. So if you go up in size, you're transferring to a larger diameter gear, then you're going to get more torque. More torque, less speed, right? Slower and more torque. Okay, so the rules that we just outlined, I know there was some math, but it's really pretty simple, right? It's just a bunch of ratios. And other than that, it's bookkeeping. You need to, the secret to understanding, gear train analysis is just working from one side to the other, right? There's a gear working against another gear, and then that works against another gear, against another gear. So you just work the problem from left to right, or right to left, whatever the system is set up. So there are some things to note. Of course, if the gears are on the same shaft, they're going to spin at the same rate. And then, as an example, if we're working from kind of left to right thing here, so the speed of this gear here, of 2, is just the first gear times the ratio of the diameter is 1/2, right? And then you can say the same thing for 4 to 3, and now you can sub in what we already knew from up here into this expression. So you just keep stacking, the math, and the equations get a little bit. I wouldn't call that long or fiddly. I've certainly seen a lot longer and fiddlier, but it's very simple. It really is nothing more than ratios. Wayne, would you do the next one? So another thing to note is that if you have 2 gears on the same shaft, they also have the same torque, right? Because there's no other place for the power to go, essentially. If you have a third or more gears there, taking torque, obviously that's not true. You need to be careful about that. So let's get Wayne, move on. So you may have heard the concept of the idler pulley. So an idler pulley, does nothing but essentially provide, some kind of, mechanical spacing, or sometimes you talk about idler pulleys with belts and things like that. It's to keep the belt tight, but it doesn't actually change the gear ratio itself. And you can, if you work out the math according to what we just were doing, you can quickly see that if you transfer speed and power, torque, speed, power, from here to here, it's completely independent of the diameter. It doesn't matter. So this guy could be tiny, he could be large. This guy's going to spin at this guy is going to spin at the same rate as this. It doesn't matter. Same power, same torque. William? Okay, so just to keep it simple, we looked at circles or cylinders, cylindrical gears or wheels, and all that was true if you had rubber wheels contacting each other. But of course, we're talking about gears usually, so gears have teeth and they mesh. The pitch diameter is effectively that diameter that we were talking about before. We don't really need to know what this real pitch diameter is. It's somewhere in between the base and overall over the teeth, because we have another way to be able to handle the calculations. We can simply just count the teeth. Next slide, please. Because the gears mesh together, right? They all have the same pitch. So the incremental spacing is the same for a given turn. So we can directly use the number of teeth as a proxy for the diameters. So the equations that we just developed with diameters can be directly used, or radii can be directly used if we simply replace the diameters of the radii with the number of teeth. So that's typically what we do. It's easy to count teeth, right? All right. So, and the last point on this slide is sometimes we talk about an efficiency, and I won't talk about it in detail here, but I have it as an example. And sometimes it's interesting to consider the differences in efficiency of the different types of gear systems that you have. For typical spur gears, like we're talking about here, it's pretty high. I don't know, probably north of 95%, something like that. Depends on some things. But efficiency is basically defined as you know, the amount of torque or power that you get out divided by what you put in, right? And this nothing is free. And
You didn't really mean torque out or torque in a transmission. I mean,
could be a transmission.
but, well, I mean, I mean, you can multiply torque, obviously it doesn't change efficiency. Efficiency always goes down with gears, right? I mean, there's.
But you're losing torque too.
Yeah, yes, I mean, but if you looked at, in this system right here, if they were the same size gears, then that would work. But if they're not same size gears, then you can have more torque out than torque in, and yet your efficiency is still less than 1.
That's true. It shouldn't be torque out.
Right.
It should just be power.
Just be power, right,
Just be
just
power.
power, yeah, yeah.
Oh, I hit it again. Sorry.
Okay,
Thank you.
yeah, please.
Yeah, and truth be told,
It works in your case when they're same size,
Yeah.
same size.
yeah.
Otherwise,
So,
it
yeah,
wouldn't.
I missed that. So,
Yeah.
yeah. You know, if life provided more time, I sat sorry, we'll get anecdotal, but last night I set out to redo this presentation, which I originally cobbled together a few years ago, and I had taken the material from somebody else. So I set out to transfer it all from Google Slides to PowerPoint, because I had some fun animations and things that I wanted to show, and they weren't working well in Google Slides. And ultimately, so I was working my way through and sanitizing everything, and you know, as life gets in the way, I quickly realized that was going to be a 4 or 5 hour task, 4 or 5 hours that I didn't have. So I went back to the.
But your point is well taken, is that efficiency affects expected torque. It doesn't affect expected speed ratios. It does affect expected torque ratios. Efficiency does affect torque. You're right, absolutely right.
Okay, thank you.
That's
Thank
right.
you for clarification. That's a great catch. All right, so wait, next slide, please. So, and I'm not going to go through a tedious example. I have the kids on the team before, and again, this is one of those things where it's nice to have, you know, in the slide deck, and if you're somebody who's going to watch the video later on and wants to work through the math, this is the best way to understand you know, everything that we've discussed so far. So it's the work problem. But basically, this is an example of a gear train, and you've got some gears that are on the same shaft, and you've got gears of different size, and you're putting power into one shaft, and you want to know, you know, basically what comes out the other end in terms of speed, torque, power. And you switch to the next slide, please. Thank you. So again, the secret to working these problems is to start at the input and to work your way through the gear train, just from one gear to the next, and it really is nothing other than, you know, the simple formula that we have already discussed. And the other thing that we could do, in addition to calculating the you know, final, or at every single gear on the system, we can calculate, of course, the rotational speed, the torque, the power. We can also calculate you know, something like the pushing force at the end, which might be the goal, right? So if we have a transmission here, and this guy, you know, we're driving, and ultimately, this outer one that's dashed represents a wheel. We might be getting pushing a force on a carpet, right? And that might be the ultimate goal of doing all of this. So, so we can calculate this at the end once we fill in the table. So William, could you please? All right, and as you see, as we move through the gear train,